All right, good evening. We are on to our very last video and very last topic for the year, which is the standard model of particle physics. So this is a great way to sum up the modern physics unit because the standard model represents everything that we know about modern physics these days. Modern physics is mostly concerned with the structure of the universe. One of the goals of physics has always been to classify what the building blocks of matter are. And over the last 100 or so years, we've really made a lot of progress with this. Today, our best picture of this starts with what is known as the standard model. The standard model is a theory which attempts to describe the most basic of all particles that compose matter and how they interact. We're going to learn a simplified version of this theory. And when I say theory, I'm not saying it as in we don't know that this is accurate. We're saying that this is our framework for how we organize all this information. We are still testing the standard model. A lot of parts of it, we have tested it. They have come out, our predictions using the standard model have come out to be very, very accurate. But there are still things that we don't quite know. You're going to need your reference tables for this. There are two charts on page 3 of your reference tables that are crucial for understanding the standard model. There's the classification of matter chart, and then there's the particles of the standard model over on the right-hand side. Here's what it means, and we have them repeated right here. All matter at its smallest level is composed of two different types of particles: leptons, Leptons, and quarks, Quarks. Very funny words, but all matter can be broken down at its smallest level into either being a lepton or being a quark, reflected here, particles of the standard model. Neither can be broken down any further than this, so we say that they are fundamental. And if you're saying, I've never heard of leptons before, I've never heard of quarks before, well, hold on. Those are names for categories of other particles. So leptons, let's start there. Leptons cannot be broken down. They're fundamental. They are typically found outside of the nucleus. Therefore, since they're found outside the nucleus, they're affected by the weak nuclear force. I know it's called the weak nuclear force, but radioactive decay can occasionally affect a lepton. They are also affected by the electromagnetic force, and the gravitational force. The only force that they do not interact with, that isn't concerned with them, is the strong nuclear force, which, remember, holds together things in the nucleus. These are outside the nucleus, so it makes sense that that force doesn't matter for them. There's 6 different types of leptons, all shown on this chart right here. One of them is a type that you've been talking about for months. A lepton, or one example of a lepton, is an electron. Okay, electrons are leptons. There's nothing inside an electron. You can't take an electron and break it apart to see what's inside of it. It's either the electron or it's nothing. Okay, there's no internal structure to it. There's some other types of leptons, though. There's 5 other types. The 2 other similar ones to an electron are called a muon, M-U-O-N, and a tau, T-A-U. Electrons, muons, and taus are all in the same row on this chart because they all are similar. They have symbols. Electron is E, muon is mu, remember the U with a little tail, and tau is a T. Well, it kind of looks like a T. It's kind of like a curvy T, kind of like this. Anyways, their similarity is that they all have a charge of -1. -1 elementary charges. However, there are other types of leptons as well. So muons and taus, we don't see them that often, but they are fundamental particles. There's nothing inside of them. We see them more when we have those big collisions at particle accelerators. There are other leptons as well. They are called neutrinos. Neutrino is an Italian word that means little neutral one. All of the neutrinos, obviously, since they're little neutral ones, are neutral. They have no charge. 0, 0, 0. You'll notice the charges are given for each of these types of particles. And the symbol for neutrino, you don't really have to know this, but it's kind of like, I think it's a Greek letter nu. It kind of looks like a fancy V, but that's a nu, and then it has either an E, a mu, or a tau next to it. You don't really need to know the symbols, and they're given there for you in the reference tables. Neutrinos are special because they have very, very small mass, to the point where we almost didn't think that neutrinos had mass at first. But it turns out that it just took us a long time to measure their mass. It's just really, 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 really small. So those are all the leptons. That's pretty much all you have to know about them. They exist outside the nucleus. They interact with every force except the strong force. There's three different, electrons, muons, and taus are all negative. And then all the different versions of neutrino, you have electron neutrino, muon neutrino, tau neutrino. They're just the three different types of neutrinos. They are all neutral and they have tiny amounts of mass. That's pretty much it for leptons. Quarks are a little different. Quarks are the building blocks that make up particles that are in the nucleus. Remember, leptons are outside the nucleus. Quarks make up the particles that are in the nucleus. As a matter of fact, quarks actually do not exist outside of the nucleus, and they do not exist, well, I shouldn't say that. They make up the particles that are found in the nucleus, but you will never find a quark by itself. It's actually impossible. It's never been done. They only exist if they're in a certain grouping, which sounds really weird. So you're never going to see just one quark by itself. There's always going to be a certain grouping of quarks. The particles of the Standard Model chart lists all of the quarks up here. And by the way, I want to talk about classification of matter real quick. We see that all matter is broken up into quarks and leptons. So we start up here with matter. We follow the arrows down. The farthest down this arrow goes is leptons. That means they're fundamental. The farthest down this set of arrows goes is into quarks and antiquarks. And I'll talk about what that means in a second. But that means that all matter can be broken down into quarks and leptons. It just so happens that leptons, they're just leptons. You can't build them into anything. Quarks can be built into some other categories of matter. So, back to the particles of the Standard Model chart. Quarks, there's 6 of them, just like there was 6 leptons. And they have kind of funny names. And just like down here, we see that it lists the name, the symbol, and then the charge. The names are kind of funny. Up, down, charm, strange, top, bottom. Okay. The reason they called them like up down is because these two quarks are kind of similar. So in some ways, or they were discovered first, I think, so that they named one up and down. Then charm and strange are kind of similar, and then top and bottom. The names of the quarks have no meaning other than that's just the name that the person gave them who discovered them. Okay, so they sound kind of silly, like charm, strange, bottom, top. Don't get caught up in the names. It's just ways to distinguish them. The symbols are just the first letter of each word. So up is U, charm is C, top is T, down is D, strange is S, bottom is B. And then it lists the charges. Now the weird thing about the charges, the thing that's probably setting alarm bells off in your head, is that every single quark has what I would call a fractional charge. Back when we first started talking about electricity, I told you that charge was quantized. It only came in certain amounts. The smallest amount of charge that you can possibly have is the elementary charge, which is the charge of the electron / the charge of a proton. I actually at the time said that there was one exception to this, but for the most part we have not seen that up until now. It turns out that quarks actually have fractional charges. I said that this was impossible to have at the beginning. It's actually possible for quarks, and we've studied this, okay? It seems like a really random result, but quarks have what we would call fractional charge. This is the only exception to the rule that a charge can never be less than the charge of an electron, but it is a notable exception. You'll notice that up quarks, charm quarks, and top quarks all have a charge of positive 2/3 of an elementary charge. Down quarks, strange quarks, and bottom quarks all have a charge of negative 1/3 of an elementary charge. Okay? That's just how it is. That's what they have been determined to have. However, I also said that it's impossible to find a quark by itself. They only exist in certain groupings. Since these have fractional charges, that's the reason they have to show up in certain groupings. When they're grouped together, then if it's the right type of grouping, then you can get a charge that is not a fraction and therefore is actually allowable. And that's the particle that exists. Okay? Any combination of quarks whose charges do not add up to a whole number is impossible to have and is not a real particle that can be observed. So, for instance, an up quark and a charm quark, if I add those two quark charges together, 2/3 plus 2/3 is 4/3. That's fractional charge. That particle consisting of just an up quark and just a strange quark, an up quark and a charm quark, cannot exist. It would not exist in nature. However, what if I have an up quark, a charm quark, and a top quark? 2/3 plus 2/3 plus 2/3 is 6/3. 6/3 is just 2 elementary charges. That particle can exist in nature. I have no idea what it's called, but that is a possibility. So sometimes people ask, well, okay, if quarks, they have all these weird rules about when they can exist, when they don't exist. If no one's ever seen a quark by itself, how do we even know that they exist? And that's a really good question. And this is going too far deep into this, but it turns out that other experiments that we have done on particles that are made up of quarks suggests that there is something inside of them. Okay, so particles that are made up of quarks, it's suggestive of the existence of quarks, and that's as far into it as I can really go. Okay, I don't really understand exactly how we're getting this information, but I trust the people who are finding it, since the results have been around for like 70 years. Okay, so quarks themselves are fundamental, but they make up other particles that you might think are fundamental, but actually are not. One type of particle that a quark can make up, if you look back at the classification of matter chart, is a baryon. A baryon is composed of 3 quarks, all grouped together. So if 3 quarks are arranged together, they create what's known as a baryon, B-A-R-Y-O-N. Baryons are fairly heavy, okay? They're fairly massive as far as particles that are made up of quarks go. One of the most common baryons is created by taking 2 up quarks and combining them with a down quark. When you create particles using quarks, you symbolize what particle you've created by combining the letters that represent each quark. So up quarks are represented by U, down quarks by D. If you have 2 up quarks and a down quark, then you have U, U, D. What would the charge of this be? Well, an up quark has a charge of positive 2e, a down quark has a charge of negative 1e. So I could add up the charges like this, plus 2/3 e, plus 2/3 e, minus 1/3 e. I hope I said that right when I said it the first time. So 2/3 plus 2/3 is 4/3, minus another third is 3/3, which is just 1. Positive 1 e is the charge of an up-up-down baryon. Now this is a special one because it's a particle that you know, actually. What particle do you know that has a charge of plus 1 elementary charges? That would be a proton. A proton is made up of 2 up quarks and 1 down quark. Here's another one that you know. Another common baryon is made by combining 1 up quark and 2 down quarks. That would make us UDD. That would be the quark composition, is how we would say it. That would have a charge of, let's see, plus 2/3 e, minus 1/3 e, minus another 1/3 e. 2/3 minus 1/3 is a third. 1/3 minus 1/3 is 0. 0 e. In other words, it's neutral. What particle do you know that's neutral? A neutron. So the only difference between a proton and a neutron is that a proton has 2 up quarks and down quark. Neutron has 2 down quarks and 1 up quark. Okay? And these are not the only types of particles that can be created using 3 quarks. These are not the only baryons. There's a lot of other weird ones that can be created by combining different types of quarks. For the most part, they are actually very unstable, though, meaning they break apart very fast and decay into other types of particles. They don't stick around that long. The only time we see them is during particle accelerator collisions. That's the only time we see like other weird baryons, like let's say an up charm top quark, or like a down strange bottom quark, or something like that. Okay, but combinations of 3 quarks are called baryons, and we can figure out the charge of each baryon by adding up the charges of each individual quark. And we write their quark composition by just taking the first letter of their names. We're going to change gears a little bit. We're going to talk about something called antimatter. I mentioned it briefly earlier in the video. The best way to think about how antimatter got proposed and then confirmed is this. If I ask you to take the square root of 4, you will very naturally tell me that the answer is 2. But that's not the only answer. Positive 2 is one answer, negative 2 is another. The actual answer here is plus or minus 2, because minus 2 squared, or negative 2 squared, would be 4. Positive 2 squared would also be 4, so the square root is either plus or minus. That's kind of like how this new type of matter got proposed back in the 20s and 30s. It was proposed and then discovered, so someone actually confirmed this. And basically, someone was solving all the equations that predicted, I think it was like the existence of an electron. And they got down to a stage where they had something like this. They had to take the square root. And they realized that not only would this propose that electrons exist, but it would also propose that a particle with similar properties but a negative sign or the opposite sign should also exist. Okay? Antimatter, they propose that this new type of matter would consist of particles that have the same mass and a lot of the same other properties as normal particles, but it has the opposite electric charge. So in other words, the first particle of this type was found to have a mass that's equal to the mass of an electron, but instead of having an electron's charge of -1 elementary charges, it actually had a positive charge. Okay, that's kind of crazy. An electron that just happens to be positive. We've never seen that before. It's a new type of matter that was proposed, and then we actually discovered it. We proposed it, then discovered it. It was crazy. We predicted that it would exist. We call this new type of matter, this new particle, it's a positive electron, so we just kind of ram those two words together. We call it a positron. And the new type of matter we refer to as antimatter. So we could also have called it an anti-electron, but positron is just a little snappier. So antimatter, by definition, is matter that has everything the same, pretty much everything the same, as normal matter, but it has the reverse sign. Okay, so that means that we can have an antiproton. An antiproton would have the same mass and same other characteristics as a regular proton, but whereas a regular proton is positive, an antiproton would be negative. There's even an antineutron. Now, the sign of a neutron obviously is neutral, so an antineutron is also neutral. There's some other differences that we're not going to get into, but even neutrons have antimatter counterparts. Every particle of normal matter, in fact, has an antimatter counterpart. It's denoted, it's shown by drawing a line over the top of the particle symbol, like this. So a positron, the symbol for a positron is the same as the symbol for an electron. Electrons are represented by little e, but we put a line over the top of it to be like, hey, that's antimatter. Okay, we're dealing with antimatter here. Even neutrons, okay, we already said this. Even neutrons have antiparticles, but their antiparticles are still neutral, but different in other, more complicated ways. So we have the existence of antimatter. Okay, we predicted it. We know it exists. It's not science fiction. There's literally antimatter produced every day in particle accelerators. Here's the cool thing about antimatter. If a matter particle interacts with its antimatter counterpart, meaning if it gets close to it, if it touches it, they do this thing where they annihilate each other. What does that mean if they annihilate each other? We use the word annihilate to mean like in sports, like, oh, we really beat them good, we annihilated them. Annihilate has a much more drastic meaning in physics. Annihilate means destroy, okay? Literally destroy. If an antimatter particle and its regular matter counterpart interact, if they touch, both particles will have their masses turned directly into energy, which you can calculate by using the equation E equals mc squared. So all you do is you put in two masses. So let's say you have an electron and a positron. You do twice the mass of an electron because you have two different particles times c squared, and that's how much energy you get out. It's turning the matter, it turns both antimatter and matter into energy at the snap of a finger. Okay? This is crazy. It's just, even if it touches, it immediately turns into energy. So imagine if you got a lot of antimatter together and it touched a lot of matter. You would have a pretty big explosion. You'd have a ton of energy being released, like the equivalent of like a weapon, literally. Matter of fact, the plot of one of the Da Vinci Code books, it's the first one, I think it's called Angels and Demons, revolves around a antimatter bomb, okay? It's antimatter that's been suspended magnetically, but if it's allowed to touch regular matter, would basically blow up a huge chunk of the location where it's at. So thankfully, we don't have a way to contain antimatter like that because antimatter usually annihilates with regular matter very quickly. You can't really build up large quantities of antimatter, thankfully, but it's kind of a neat science fiction concept. Kind of a scary one as well. The nice thing is, antimatter and matter annihilating only happens for particles meeting their direct antimatter counterpart. It doesn't happen if, let's say, a positron meets a proton or an antineutron meets an electron. It has to be a particle and its direct counterpart. So a proton, antiproton, electron, positron, antineutron, neutron, top quark, anti-top quark. Okay, it wouldn't happen if it was, for instance, like a top quark and an anti-down quark. And as a matter of fact, there is a special branch of matter called mesons, which actually are composed of a quark and a different antiquark. Those are called mesons. So the other type of particle that can be formed with quarks is known as a meson. These particles are usually lighter than baryons. Mesons are composed of a normal quark, meaning normal matter, and an antiquark, meaning a quark made of antimatter. Meaning same mass, same other properties, different electric charge sign. One example of a meson is a particle known as a pion, and mesons are very unstable, just like some of the other exotic baryons. Protons and neutrons are stable. All the other baryons are kind of not stable. They decay very quickly. Anyways, mesons are also, they decay into other stable particles very quickly. Mesons are composed of up quarks, well, one up quark, I should say, and an anti-down quark. So just to give you an idea of how the signs work here, an up quark charge is positive 2/3 E. An anti-down quark, a normal down quark, is negative 1/3 E, but anti-down would be positive 1/3 E. Which gives a pion a charge of plus 1 E. Plus 1 elementary charges. Okay, those are how mesons work. You don't have to know too much about them other than they're composed of quarks and antiquarks. Not the same, not a quark and its direct antiquark counterpart, those would annihilate, but instead a quark and a different antiquark. All right, last thing, our last category, both baryons and mesons can be classified as hadrons. Hadrons are basically anything made up of quarks, okay? Leptons are separate. They don't stack on top of each other. They don't build into anything else. Quarks build into baryons or mesons, but we classify both of those as hadrons, Hadrons. Hadrons are particles that are made up of quarks. Hadrons are typically found in the nucleus. They interact with all four fundamental forces, including the strong nuclear force. They do not, that's in opposition or in contrast to leptons, which do not interact via the strong nuclear force because they're not in the nucleus. Hadrons are in the nucleus, leptons are not. And with that, we are officially done with our physics curriculum. I've had a good time making these videos. I hope they've been informative so that we can get things done in class and have more fun in class and do lots of activities. That's why I've been doing these videos. I hope that over the course of this year you've learned some good physics, and I would love it if you took some more physics courses with me, such as AP 1 or 2, or even took some physics courses in college. And if that's not in your future, I hope you learned a little bit about how the universe works. And even if you didn't do that, I hope you learned something about, hard work and perseverance. Nothing good in life comes without hard work and perseverance. And even if you didn't like physics, hopefully you persevered through it. Hopefully you tried and you built up some, good character and work ethic. Not that you didn't already have it, but making it to the end of this course, you've really done quite a good job. This is not an easy course, and I congratulate you on it. So, with that, I'm all done with my videos, and it's been a blast. Thank you guys a lot, and I'll talk to you later.